SwayamPrabha. Digital India. Educated India.
Okay, so let us continue our discussion from the previous module. So today now we are going to start module 3. Okay, so module 1 and 2 are completed. So we are extending our discussion from module 3, which I have named as deformation of sheet in plane stress. Deformation of sheet in plane stress. So this is actually a small module. So in this we are going to discuss about some theoretical and some practical aspects. Okay, and some calculations, like that. Okay, so to start with, in the previous chapter we were discussing about we can evaluate strains, principal strains epsilon 1, 2 and 3, which is going to depend on the initial and original dimension of a particular element. We worked out some two problems also in the previous chapter, right. So now then further strains, if you calculate, you can calculate effective strain, then effective stress by knowing some flow stress model. From effective stress by knowing an yield function, you can get sigma 1, and by knowing beta alpha, you can get sigma 2. Okay, so from there onwards, you can get hydrostatic stress and principal stress, deviatoric stresses. So all this can be calculated along with the work done. That's the way we started, right. So now the first important thing is to evaluate the strains at different locations of a sheet. So how do we do it practically? So we start with that discussion, and then we go ahead with some important aspects in this particular chapter. So now, so here I have given 3 figures, A, B and you have C. Okay, so you can imagine that A is basically an undeformed sheet. Okay, this is basically an undeformed sheet, and this is a deformed sheet. Okay, and this is a deformed sheet, and this is a deformed sheet. Okay, so now the question is, how do you calculate your strains? So if an undeformed sheet of thickness T naught, let us say initial thickness T naught, is marked with grid of circles of diameter D naught, okay, so or a square mesh or a square grid of dimension, let us say D naught, okay, then during uniform deformation the circles will become ellipse, okay, with major and minor diameters as D1 and D2. Correct. So what does that mean? That means suppose you have a sheet, through which, using that you are going to do deep drawing or stretching or any sheet forming operations. First of all, you have to put lot of circles on the sheet surface. Okay, you have to etch or you have to print several circles of known dimensions. Say for example, this D naught. Okay, so I have just given you some example 4 circles, 1, 2, 3, 4 of diameter D naught. D naught could be maybe about let us say 20 mm, let us say 2 centimeter, you can say 20 mm. Okay, so let us say 2 centimeter, you can say. Okay, so small circles you can put, okay, or maybe like 10 mm circles, like which is 1 centimeter dimension, like that you can put, okay, small dimensions, okay, and smaller the diameter of the these grids, you can calculate strains at a very localized region. Okay, that's a thing. Okay, so I just given you a reference, okay, like this, so you can look into different standards how to do it. So anyway, so now given a sheet where you are going to put lot of circles on the sheet surface, okay, and what will happen to the circles when you deform it? It is going to become an ellipse like this, depending on whatever beta or whatever alpha you are going to deform it. Okay, so D naught is going to become D1 and D2, and D2 we are going to call it as your minor axis, which is nothing but minor diameter, and D1 as major diameter. Okay, so sometimes what we do is instead of circles we can put square also, square grids are also possible, okay, which is going to become D1 and D2, like a rectangle or any other distorted rectangle you can have, but it's always better to put grids of circles. circles. Okay. So now what will happen? Okay, so given deformation or alpha and beta, this ellipse is going to have some dimension. Okay, you will get d1 and d2, and from d0, which is original dimension, you can get epsilon 1 and 2. So epsilon 1 is going to be ln of let us say your d1 by d0, because the major, no. So let us say you have major and minor axis. So epsilon 1 is let us say d1 by d0, and epsilon 2 as ln of let us say d2 by d0. Okay. So you have to be a little bit careful in which orientation you are going to pick up these two strains, but we have seen some examples, accordingly you can take it. Okay. So now the new thickness T and the deformation stresses are sigma 1, sigma 2, okay, which are also referred here. So this has become T, small t, and you have sigma 1 and sigma 2. These are two principal stresses acting on the sheet, which is responsible for deformation. Okay. And this sigma 1 sigma 2 will give rise to T1 and let us say T2, which are actually called as a tension or traction. Tension or traction. Okay. So that T can be evaluated from sigma into T. Okay. If you want T1, it will be sigma 1 into T. If you want T2, it will be sigma 2 into T, which is what I have given here. Okay. T is known as tension or traction, which means it is always pulled in one direction. Okay. Suppose in principal direction 1 you have T1, that is sigma 1 into T, assuming T to be a constant value, new thickness but constant. Okay. Sigma T1 is equal to sigma 1 to T, which is nothing but major tension, generally it is positive in nature. Okay. And you have T2, which is sigma 2 into T, which is generally called as minor tension. It is positive in stretching, but opposite negative when you go for compression type of deformation. Okay. So T can be found out as sigma into T. Okay. So now you know how to calculate epsilon 1 and epsilon 2, and from there you can calculate epsilon 3 or you can directly calculate T by T naught. Okay, with respect to this figure you can get epsilon 3 is equal to ln of T by T naught. We have seen some examples before in the previous chapter. Okay. So now such evaluation of strains will give you something called as a strain distribution, okay, in the entire deformed sheet, which will give you some important information during the deformation process. Okay. So what do we do? Say for example, you take a deep drawing. I just given you as example of cup deep drawing, cylindrical cup deep drawing. Okay. So you have a blank and you have punch, you have die, and there is a blank holder. So you know what is the meaning of blank holder. Blank holder is going to hold the sheet between the die and the blank holder, and you are going to give some force. Let us say you give a force of BHF. Let us say a blank holding force is given here. Okay. And you know that there is no restriction for the movement of sheet in the radial direction. It moves actually, okay, but only restriction is through friction. Okay, there is otherwise there is no constraint. So finally you are going to get a cylindrical cup like this. You have seen this example before. Okay. So now I have a partially drawn cup. Okay, similar diagram we have seen before. I have partially drawn cup. Okay, I have just shown you one sector of that. So this you know is a flange region, this is a cup wall region, and this is a cup bottom region. Okay, that is known to you. So now we want to evaluate strain. Now we are going to pick up this deep drawing as a process. We are going to evaluate strain at 6 different locations, 1, 2, 3, 4, 5, 6. Okay. So we are starting from cup center to the your punch corner, then in the cup wall, then in the die corner, and somewhere in the flange and at the edge. 6 different locations we are picking, and you imagine that this entire sheet on the sheet surface from top view, if you see, okay, on the sheet surface is going to be a sheet is going to be a circular one, and there are a lot of circles printed on it, and you are doing deep drawing, and you are going to pick up these 6 locations to get strain distribution. Okay, and that's what they simply referred as we evaluate strain in all these locations and by measuring the grids. Okay, and I can plot a graph between epsilon 1 and 2. Okay, epsilon 1 and 2, and you should note down here that epsilon 2 can have negative and positive value, and epsilon 1 we are keeping always as a positive value. Okay. So epsilon 2 is in x-axis and epsilon 1 is in y-axis, and you are going to calculate all the strains, and you are going to plot here. I have shown 2 different stages. Okay. So this is your stage number 1, and this distribution is for stage number 2 at 6 different locations. So it starts with the edge. This edge is here. Okay. It starts with the edge and it moves to a center. So this is your center of the cup. Okay. So you can see that maybe in the stage 1. Okay, let us pick up stage 1, okay, which has got the lower strains as compared to stage 2 naturally. Okay, and stage 1 is center location. You have strain here, and then the the third location is somewhere on the y-axis, okay, and the fourth location is here, fifth location is here, and the edge it is somewhere in the negative epsilon 2, okay, probably beta is going to be minus in that. So now if you further deform it and the same location, same grids, I am going to monitor the new dimensions, new diameters, and I am going to get epsilon 1 and 2, and I am going to plot here in the 6 different locations, and you will see that this is the second stage. So what do you get from this? You can get the present status of deformation in these 6 different salient locations. 6 different salient locations, and 6 different locations will have 6 different betas and alphas. You can see this dotted line tells, let us say this is one beta, this is another beta, this is 1, 4, 5, 6 different betas you can imagine. Okay, this will give you the entire feel for how strain is getting distributed in this. And when you compare first stage and second stage, the regions are not equally deformed. The regions are not equally deformed. You see that? So here the strains are closer, and when you move towards the edge, it is deviating a lot. It is deviating a lot. So it will also tell you which location is going to deform significantly as compared to the other locations. Okay. So such a strain distribution can be evaluated for any sheet deformation or even for tube deformation process also, to get an idea where you are going to have what type of strain distribution, where you are going to have strain localization, which is going to be responsible for, let us say, instability or fracture, which you are going to see later on, or necking, like that. Okay. So I just summarized whatever I have discussed with you here. Okay, the strains are located at locations mentioned in figure B. The strains are plotted on these locations. Okay, on these locations. Okay, in strain space epsilon 1 and 2 graph, and strain locus can be obtained in a particular stage. So this is called as one strain locus. This is called as another strain locus. Same location, 2 different stages. You can also have third stage, which could be something like this. So fourth stage, fifth stage, something like that, until you have a full cup form. Okay. The strain locus may expand uniformly till a stage, and later some points may stop straining. Okay. Then a process limit is reached. That is what I gave an example. Probably this region will stop straining if you further deform it, because the strain gradients are very low here, but here you will see that there is significant deformation going on in these locations. Okay. So this typical strain pattern is called as a strain signature. Okay. This strain signature can be obtained for different processes at different stages, and there are certain advantages of that. Okay. So just to summarize, how do you calculate the principal strains? You have epsilon 1, which is nothing but d1 by d naught. Epsilon 1 is d1 by d naught. What do you write? Right? Yeah. So epsilon 1 is d1 by d naught, epsilon is d2 by d naught, and epsilon 3 is ln of t by t naught, or you can get it from epsilon 1 and 2 at a particular location. Like this you are going to get for all the grids. Okay. So now if you know epsilon 1 and 2, okay, so then you can get beta. That is why we have 6 different locations, 6 different beta, 6 different strain ratios or strain paths. Epsilon 2 by 1, 2 is d2 ln of d2 by d1 divided by ln of d1 by d naught. Okay. And if beta is a constant, we call that as a linear strain path. What do you mean by strain path? Strain path is nothing but the mode of deformation. Okay, nothing but the mode of deformation. So strain path means this is one strain path. Okay, let us say you are going to pick up from 0. Okay, this particular element is following this particular strain path, like this. Okay, essentially beta. Okay, that is considered as linear. It is not going to change. It is not going to become non-linear. If it becomes non-linear, which can happen, then you have to be a little bit careful. There is something happening when there is a change from one slope to another slope. You have to be careful. Okay. So how do you get epsilon 3? We are actually summarizing what is required for such strain signature. So epsilon 3 is ln of t by t naught, which is equal to nothing but minus of 1 plus beta into epsilon 1, which is again equal to minus of 1 plus beta into ln of d1 by d naught. Okay, so you do not need to measure this, rather you can get d naught, which is known to you, okay, let us say 10 mm, and let us say you have d1, you can measure it and get it. So beta is fixed, okay, so you can substitute it and you will get epsilon 3. And from epsilon 3 you can get the current thickness, which is nothing but t naught exponential epsilon 3 or t naught exponential minus of 1 plus beta into epsilon 1. So epsilon 3 you can substitute it here. Okay. Alternatively, you can get T as volume remains constant, okay, in a particular grid. Okay, you can get this equation, and from there onwards you can get T. T is nothing but T naught d naught square divided by d1 d2, where d naught is nothing but diameter of the initial circle grid, and T naught is the thickness, original thickness at that location, and d1 and d2 are the new dimensions of that ellipse. That will give you T. So, either you can get T from this or you can get T from this. So, the entire summary of this is you can get just by putting circle grids, you can get epsilon 1, 2 and 3, okay, and you can plot it at any number of locations, which will give you a strain locus or strain distribution in the entire section, and that will give you some idea of what type of deformation you are going to have, and whether it is equally deforming at different stages or it is going to be different type of deformation, different locations that can be obtained. Okay. This I think I told you, okay. The whole summary is this, assuming beta to be constant. Okay. Beta can change, okay. Beta can change. Okay. So, now let us come to modes of deformation. We will give some take more ideas into these modes of deformation, or modes of deformation is nothing but beta or alpha. Okay. So, what all the information that we are going to get from this? Each point in the strain diagram indicates the magnitude of final, major and minor strain and the assumed linear strain path to reach this particular point. Right. Suppose you pick up this particular point, let us say, okay, this is again a plot between epsilon 1 and epsilon 2, correct. Let us pick up this particular point, let us say A, okay, it has got a magnitude of epsilon 1 and epsilon 2, assuming this linear strain path to reach that particular point. Same way for OB, OC, OD and OE, right. So, now this ellipse which I have shown here, okay, is nothing but a contour of equal effective strain, epsilon bar. Just to give some idea, it is a contour of equal effective strain, okay. It is a contour of equal effective strain. That means you deform the sheet along OA and you stop here, OB you stop here, OC you stop here, OD you stop here and OE you stop here, and they have to be stopped at almost the same effective strain, okay, and then you join it to create a contour, okay. So, and from the work hardening hypothesis, they will all have same sigma f at that particular location. Okay. So, the ellipse shown in the contour is a contour of equal effective strain epsilon bar, each point on the ellipse will represent strain in the material element that from work hardening hypothesis has the same flow stress sigma f. Okay. Anyway, so that is just one small information, but what is very important for us is what does this signify? OA, OB, OC, OD and OE. That is what we are going to discuss now in the next this particular sections. So, before discussing, just get a some idea from this diagram. So, this anyway is a plot between epsilon 1 and 2, and you will see that I am representing OA path, which is denoted by beta is equal to 1. Okay. That means epsilon 2 by 1 is equal to 1. So, epsilon 1 is equal to epsilon 2. Okay. And here OB, when you go along this path, you are going to have beta is equal to 0, okay, which is nothing but epsilon 2 0, which could be called as a plane strain process, okay, because as I already told you, when you have OA this particular point, okay, there is one epsilon 2 and 1 associated with this point A, and there is epsilon 3 inside that. Okay. So, epsilon 3 has to be calculated from this location epsilon 1 and 2. So, epsilon 3 exists inside. Okay. So, which means that you can call this as epsilon 2 as 0. So, that is why you have only epsilon 1, but epsilon 3 exists. So, you can call this as a plane strain deformation. Okay. Similarly, OC you can say beta is equal to minus half, OD you can say beta is equal to minus 1, and OE, which is also a critical strain path, beta is equal to minus 2 we get. And you can also see how these ellipses are going to, how the circles are going to get deformed. So, here the circle will become a larger circle, okay, so that if you get beta it will be equal to 1, right. So, this dimension d0 is known to you, okay, and the new dimension, let us say this d1 comma d2 both are same, comma d2 both are same. So, you can calculate your epsilon 1 and 2 from the previous formula, okay, and you will get the strains to be same, that is why beta is equal to 1. If you come to this particular plane strain, you will see that it is going to become ellipse, but the minor axis will be same as that of your circle, that is why you have strain to be 0 in that direction, but otherwise you have epsilon 1 and epsilon 3. And here onwards the ellipse is going to be inside the circle. Okay. So, you can see ellipse has gone inside, further inside and further inside. Ellipse is actually getting compressed, okay, in the width direction. What is this thin and thickens? We will come to this after this particular discussion. Okay. So, now there is a limit for this beta. There is a limit for this beta. Beta generally changes from 1 to minus 2. Okay, that is what I am saying. Beta is equal to 1 is one limit, beta is equal to minus 2 is another limit, okay, and in between you can have any number of betas depending on what deformation you are going to do, but we are just shown here 5 different betas. Okay, 5 different betas, 1, 0, minus half, minus 1 and minus 2. Okay. So, now let us go into some important details about this each strain path OA, OB, OC, OD and OE, and where do you see this type of situations, that also we can have to some extent we can have some idea. Okay, let us go for point A. Point A is along, that means you are picking up OA path. Okay, you are picking up OA path, this path. This path is actually called as balanced biaxial stretching or equal biaxial stretching. Okay, we call it as beta is equal to 1. Okay. So, what are the salient features in this? This beta is equal to 1 can be seen in this type of situations. Okay. What is the situation? Situation is there is a circle and circle is going to become a bigger circle. So, it will become a concentric circle. Okay. So, and you will see this type of situation in a circle which is inscribed on the uppermost point when you do this kind of deformation. Like there is a sheet which is kept in a blank holder. Okay, and the punch is getting displaced here and your sheet is getting deformed here, right. So, this is the height of deformation, this is your height of deformation, this much it has deformed, and you will see beta is equal to 1 situation somewhere in the mid portion, in the uppermost portion, that is the pole region. That element is actually, if you put a circle on that particular location, it is pulled equally in both the directions. So, it will be like this. Okay. So, beta is equal to 1. Okay. What will happen to thickness strain? Thickness strain can be obtained. So, if beta is equal to 1, what is thickness strain? So, thickness strain with beta, what is the equation we have? We have this equation, isn't it? So, thickness strain is equal to minus of 1 plus beta into epsilon 1, correct. So, beta is, let us say, we say 1, isn't it? So, 1 means minus 2 epsilon 1, epsilon 3 is equal to minus 2 epsilon 1. What does it mean? That means, so you have a particular strain, okay, and your thickness is going to decrease rapidly with respect to your strain in principal direction 1. Okay. So, it is minus 2 times of minus signifies that thickness strain is negative, which means you are going to have thinning, and twice means the thickness is going to reduce more rapidly with respect to epsilon 1. Okay. So, epsilon 1 is like in that location epsilon 1 you can get from D0 and D1, D2, but for a particular epsilon 1, okay, if that element is actually stretching like this, then you will have thickness decreases more rapidly as per this particular equation, twice, it is going to decrease twice. Okay. And there is one more important feature that we need to understand, epsilon bar is equal to 2 times epsilon 1. Epsilon bar is equal to 2 times epsilon 1. So, how do you get the moment you go for epsilon bar, which is nothing but your effective strain, by using von Mises equation? We already derived this. Okay, we already derived this equation in the last section, and you can put beta is equal to 1 here. So, this is going to be 1 1. So, 3 will be cancelled, it will be, yeah, so 2 into epsilon 1. Okay. So, epsilon bar will be equal to 2 into epsilon 1. What does that mean? That means the sheet is going to work harden rapidly with respect to epsilon 1. So, you give strain in principal direction 1 and you calculate it, but you will see epsilon bar effective strain will be twice than that of that. Okay. So, now you can get epsilon bar from this, and sigma bar is equal to k epsilon power n, you can substitute for a constant k and n, you can get sigma bar. Okay. So, and you will see that the sheet work hardening is going to be rapid in this particular type of deformation. That means you have a sheet that is a component that is made, okay, and at one particular location, let us say a set of elements are deforming in equibiaxial stretching a strain path where beta is equal to 1, then in that location you will see thinning is going to be significant and work hardening is also going to be significant. Okay. So, with respect to what? Because when we are saying thickness strain is going to be thickness is going to decrease rapidly and strain hardening is going to be rapid, no, with respect to what? With respect to epsilon 1, but then we are also comparing with other strain paths. Let us go for point B. This point B, okay, is like this. So, wherever you have this OB strain path, you will see that if there is a circle will become an ellipse, but the change in dimension in this direction, okay, is going to be negligible. So, it will remain as a plane strain type of analysis. It will become plane strain. So, where is OB in this diagram? OB is here. You go along y axis, but epsilon 3 is there inside. So, here epsilon 2 by 1 is equal to 0. So, epsilon 2 is 0. So, epsilon 1 will be equal to minus epsilon 3. Okay. So now here I just simply made a circle expands only in one direction and circle becomes ellipse in which minor axis is unchanged like this. And you can see such situation in a channel, a side wall you can say. Okay, suppose this is a channel, sheet channel that is made, okay, channel type of deformation. Okay, you will see somewhere in the cup wall region you may see that kind of situation. Let us come to point C, path OC. Path OC is what? Path OC is this path beta is equal to minus 1 by 2. This is known to us. Beta is equal to minus 1 by 2. For that alpha is going to be 0, which means it is a uniaxial type of deformation. It is uniaxial tension. We have seen that predominantly. So when sigma 2 is equal to 0, like in the uniaxial tensile test, that is the situation you see here. Okay, that means your sheet stretches in one direction and contracts in the other direction. So ellipse has started going inside the circle dimension. And generally you can see such type of situation exists in the whole expansion test at the edge. Okay, so one has to really look into it, but some idea you will get from this kind of application. Okay, you can see suppose a hole is stretched, actually pushed in this direction, you may see this kind of situations here. Point D, this point you already discussed in one of the problem, your point D, that means you are following path OD and you are reaching this point D, okay, which is described by beta is equal to minus 1. Okay, this OD path is also called as drawing or constant thickness process. Constant thickness process. I think constant thickness process, this example we have seen in the second problem of the previous module, isn't it, where we are trying to compare two different betas, right. One of that is basically drawing or constant thickness process. I also referring to the calculation and say that epsilon 3 is 0 there, which means thickness is not going to change at all. And you will see in such cases ellipse is going to further compressed inside, okay, in the your minor dimension side. Okay, the minor dimension it has gone, is further compressed, and you can see such situation existing in the flange region of the cup that is formed. Okay. So here you will see that the principal strains are equal and opposite. Epsilon 2 by 1 is equal to minus 1, so equal and opposite. Okay. So observed in flange region of drawing, that is what I was telling you, and work hardening is gradual. Work hardening is gradual, how will you find out? Okay, you will see that here. Okay, so before that you can find out epsilon 3 is equal to minus of 1 plus beta naught epsilon 1 and beta is equal to minus 1. So epsilon 3 is going to be 0. What does it mean? That means if you deform a material in this particular strain path, you can deform the material up to a particular strain, but without much change in the thickness. So thickness strain is going to be almost 0. Okay, so now for this also you can get epsilon bar, right. So what is epsilon bar? Epsilon bar is this equation, and your beta is equal to minus 1 you put here. So 1 minus 1 plus 1, okay. So square root of 4 by, so 2 by square root of 3 into epsilon 1. So 2 by square root of 3 into epsilon 1, which is nothing but 1.155 times epsilon 1, and when you compare this with the previous fellow, that is your 0.8, it is 2 times of epsilon 1. This is what I was telling you. If you compare these two processes, epsilon bar is equal to 2 epsilon 1 and epsilon bar is equal to 1.155 times epsilon 1, and you can say that here work hardening is actually very gradual. In the other case, when you go for balanced biaxial stretching or equibiaxial stretching, this is going to be rapid. Okay. So one has to be very, very careful in this type of deformation, which deformation you are going to pick up. And there is one more point called as point E. Okay. And if you pick up a point OE, that is the least one, okay, minus 2. Okay. Here also you can see that epsilon bar will be equal to minus epsilon 2, and of course you can also get this type of relationship. Okay. If you put a sigma bar equation, square root of 1 minus alpha plus alpha square into sigma 1, isn't it? It's there. If you put you can get sigma bar, and you will see that it will be equal to minus sigma 2, and epsilon bar equation can also be obtained. Beta is equal to, let us say, minus 2. Beta is equal to minus 2, 1 minus 2 plus 4 minus 2, 2, okay, into this one. So you will get minus epsilon 2. Epsilon bar will be equal to minus epsilon 2. So now there is one more point to this here. This point E is generally seen in the edge of the flange. Okay, we call it as uniaxial compression. That means the ellipse is going to further compressed in the width direction. Okay, and this is actually a location where sheet is going to thicken. Okay, we have seen one example, no, in the first problem where sheet thickness is actually a little bit increased. Okay, so I think initial thickness was 0.8, and after calculating the new thickness, it was 0.838 or 0.84 like that. So which means the sheet thickness has increased. That type of situation can come probably at the edge of the this flange, and you have to be very careful with part OE because that can create wrinkling. Okay, it is pulled in one direction and pushed in this direction, no. So in plane, right. So what will happen? Now the sheet will try to move up out of plane, okay, which is what you are going to call it as a wrinkling on the flange region, which is a defect actually, which is a defect. That's why you are actually providing sufficient blank holding force to suppress it, okay. So that will happen here, okay. So these are the 5 important modes of deformation, okay, beta or alpha you can say. Of course, now we are going to see how to get alpha from beta, and all this beta is going to have different situations, okay, from OA being equibiaxial, okay, then you have OB which is plane strain, then you have uniaxial, then you have drawing, then you have uniaxial compression. Okay, these 5 are going to be important, and of course you can have any strain paths in between. In between also you can have any strain paths to pick up your deformation. Okay, so now there is one more point in this diagram. I have copied the same figure here, epsilon 1 versus epsilon 2. In this you will see you can divide this beta into 2 parts. Okay, one beta greater than -1, one greater than beta greater than -1. That means -1, -2, 0 and 1. In these strain paths, if you see, the material will actually thin down. Okay, material will actually thin down. Okay, and beta is equal to -1 is a transit. Okay, is a transit region, and that is why you have 0 thickness strain. That means it's not going to thin, it's not going to be thickening. So no thinning and no thickening. Okay, this is a transit region. And if you go on this side, right hand side, okay, of this diagram, then you will have a thinning in all these strain paths. And if you go on this side of beta, that means your beta less than -1, that's between -1 and -2, you will see the sheet becomes thicker. You will see the sheet becomes thicker. So beta, with respect to beta, you can divide the sheet forming deformation into rather 2 parts. One is those deformation process which involves thinning, and that will be beta greater than -1 this side, okay, and the other part is actually beta less than -1, which is going to be sheet getting thicker. Okay, so now we will come back to this after this discussion. So now this part, this small part, we are going to discuss about different effective stress strain loss. Okay, so effective stress, effective strain loss means how do you relate sigma bar to epsilon bar. Okay, so 1 or 2 equations we have already seen, okay, but we will see that in the effective terms. Okay. So the first law that we are going to see, and we have already seen this several locations, including problems, that is nothing but sigma bar is equal to k epsilon bar power n. It's called power law. It's called power law. Okay, and this equation is predominantly used in all the calculations, and we have also used this equation, similar equation, in our problem also, when you are trying to find sigma bar from epsilon bar. And you remember sigma bar can be related to sigma 1 and sigma 2 by any yield function like von Mises yield function, which you already derived. Okay, so now you know how to find k and n from this, right? So standard procedure is there. You do uniaxial tensile test, get the load displacement graph, convert that into true stress strain data, right? So and for isotropic material, we say that effective stress strain curve is going to be coinciding with uniaxial stress strain curve that we already derived. Okay, sigma bar is equal to sigma 1 and epsilon bar is equal to d epsilon 1 or epsilon 1 we already discussed. So if that is the case, then you can get k and n from the slope of natural logarithm plot of sigma versus natural logarithm plot of epsilon, and that will be n, and the intercept will give you k value, correct? So now if you substitute this equation is ready. Let us say sigma bar is equal to 200 epsilon bar power 0.25, means by giving different epsilon bar values, you can get different sigma bar values, and that can be compared with experimental data like this. Okay, and depending on how you fit, you will have agreement between these two curves. Okay, but there is one problem to this. Problem is, for 0 strain you will have 0 stress. For 0 strain you will have, let us say, 0 stress. Okay, it does not predict the actual yield stress. What does it mean? That means suppose the material is already undergone some deformation before coming to tensile test, that means the material is already hardened to some extent, isn't it? That will not be captured by this fit, this equation. Why? Because when you put epsilon bar as 0, you will get the strength as 0. So, that means it is going to start from here, okay, as if like there is no yielding happened. Okay. Actually, there is a initial yielding that has happened, which is going to actually start from here, which will not be predicted by this particular power law, but still it is predominantly used. Now, to capture that, the change in strength when you do tensile test, you introduce something called as a pre-strain. Okay, this is what we used it in the previous problem as probably 0.008 or 0.0008. That's a small value we used. Okay, it's generally a small value. Okay, so now if you put epsilon bar as 0, you will see that there is a small effective stress staying with that material, and they may coincide somewhere here. Okay, what is the physical meaning of this? This pre-strain, the meaning epsilon bar is called as pre-strain. Okay, it is going to take care of the materials hardened in the pre-air process. If the material is hardened or not in the pre-air process means, let us say for example rolling. Okay, the material is rolled and then you are going to characterize its tensile properties. Okay, or several stages of deep drawing, let us say there are 7 different stages of deep drawing. That means with respect to second stage, first stage is pre-air formed. With respect to third stage, there are 2 stages before. So, how do you capture the change in strength? One way is to model the stress strain behavior using this equation. Just by putting this constant epsilon naught, it is going to capture the initial strength of the material, and the physical meaning of epsilon naught is this difference. Okay. So, you will see that this epsilon naught is such a small strain that you are going to give, and if epsilon bar is 0, it is going to start with a particular strength, which is nothing but the yield strength of the material, which actually is equivalent to the material it's already hardened ability before process, in the pre-air process. So, but in this, how do you get K and N? K and N can be obtained by fitting it. Okay. So, what you can do is like you can use this equation, okay, to know K and N that you know already, and you can use that K and N here, okay, and calibrate your stress strain data such that your experiment and the data from this equation are going to match. There will be one particular value of epsilon naught from each at which you are going to have very good agreement between these two. That could be the value of epsilon naught. But how to get K and N? K and N you can get from the other hardening law, sigma bar is equal to K epsilon bar power N. Okay. These two are other simple equations, generally we do not use these days. Okay. So, again you can see the plot. Actual stress strain behavior is this only, the dotted ones are actual stress strain behavior, you can say from experiments. Okay, you can say this is from experiments. Okay, this also from experiment. Okay. So, now you can have an equation sigma bar is equal to y plus p epsilon bar. So, when you have strain 0, sigma bar is equal to y, and that is this point, which is nothing but your yield strength. Okay, it starts from yield strength, but it is not going to have a power law based strain hardening behavior. It is going to vary linearly with the strain, and the fitting is going to be varying significantly at different locations. You can see the difference. But if you do not have any material constant, one can use it. The fourth one is further simple, sigma bar is equal to y. This is also called as rigid perfectly plastic model. So, your actual experimental curve data point is this, but you are modeling it with a horizontal line which is equal to sigma bar is equal to y, and this is nothing but your y only, nothing but the yield strength, and it is not going to harden at all, okay, which is called as rigid perfectly plastic model. So, these are 4 equations one can use, but other than that there are several other forms of equation. Okay, there are maybe another 4 or 5 important forms are there, one can look into literature for that, we are not going to discuss it here. Okay. And just to complete this particular discussion, okay, so here what I have done is for different betas which I have already seen, okay, 1, 0, minus 1 by 2, minus 1, minus 2, we can calculate alpha, isn't it? So, that alpha relationship with respect to beta isn't it? So, we already derived it using Levi-Masser's flow rule, isn't it? So, in that way you can calculate different alphas, and you will see that for equibiaxial stretching, this is 1 and this is also 1, plane strain, this is 0, this is 1 by 2, uniaxial tension, this is minus 1 by 2, this is 0, for drawing it is minus 1, for uniaxial compression it is minus 2, and if you convert that into for alpha it is going to be minus infinity. Okay. So, now this diagram can be converted to this diagram. Okay. This diagram is, we already know, it is basically nothing but a plot between epsilon 1 and 2. Now, I want to convert that into sigma 1 versus sigma 2, which is our well known yield locus, Okay, since we are speaking more of von Mises type, then it will be in the form of an ellipse. Of course, sigma 3 is 0, it is plane stress process. Okay, so and the same paths are noted here. OA, OB, OC, OD and OE are noted here. OA, OB, OC, OD and OE, but you have to be very, very careful in comparison. Okay, OA will have almost the same location of what you see here, isn't it? Because both are 1. Okay. So now, of course, you know that this element is actually pulled equally in both the directions. So alpha is equal to 1. So now you pick up OB. OB is actually coinciding with y axis, which is a plane strain mode of deformation. Okay. For that, if you get alpha, it is not going to coincide with y axis. We have to be very careful. It is going to be little on the right hand side of y axis. That is your OB. Okay, where alpha is equal to half. It is also pulled in both the directions, but in different proportions. OC, if you pick up, it is on the left hand side of y axis here in the strain diagram, but that is going to coincide with y axis here. Why? Because your alpha is equal to 0, which means your sigma 2 is not there, okay, and sigma 3 is anyway not there, and you are going to have, along the y axis. And here you will see that it is actually pulled in only one direction. Okay. So OD here and OD here are looks same because it is -1, okay, and you will see that the square element is actually pulled in one direction and pushed in other direction or compressed in other direction, maintaining alpha is equal to -1. Okay. So you have to be a little bit very careful in this. Okay. So I think when we discuss about yield locus, I shown some example of different locations of yield locus with respect to deep drawing, and I was referring there in the yield locus we are referring to plane strain, right. So you have to be a little bit very careful that this plane strain OB is actually here, in your sigma 1 sigma 2 plot. This OB is actually plane strain, is actually OB here. Okay. So the last one is actually purely compression, that is along the x axis, okay, when you have sigma 1 and sigma 2, which is going to beta is equal to -2. Okay. So in this way you can convert all this betas into alphas. Okay, we have done some numerical problems also where you have, once you got beta you can get alpha, and these are the 5 prominent alphas and betas through which you can deform material to any strain. You can have in between also, it depends on the material, okay, and what type of deformation you are giving. You can have in between these two, you can have between plane strain uniaxial to drawing to uniaxial compression. Okay. So you can have a variety of values in this. Okay, and this can be separated, and this can be separated as I was telling you. One is going to be thinning, and that is beta in this side, beta this side, beta greater than your -1, beta less than -1 will be divided into 2 parts, one for thinning, one for thickening, like what we discussed here, this slide. So, okay. So we will stop here and we will continue our discussion further.